Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on thermal metamorphism of basic or mafic rocks. Under the following heads: Introduction, Thermal Metamorphism, Characteristic Minerals, Type of Protolith, Metamorphism of Basic or Mafic Rocks with the help of ACF diagram for individual phases: Albite epidote hornfels phases, hornblende hornfels phases, pyroxene hornfels phases, and sanidinite phases. Pressure temperature condition and summary. Hope it will be useful for you. Try to be regular in course. Temperature, we can divide the metamorphic phases into three types, mainly the phases of low pressure, phases of intermediate pressure, and phases of high pressure. Mayosiro originally recognized three different phases series. First, a geolite, prehenite, pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized by green schist, epidote amphibolite, gaunlite type, characterized by paragenesis of kyanite, selemonite type, and an Abukama type of green schist, amphibolite, gaunlite, characterized by the paragenesis of andalusite, selemonite type. Phi et al. In 1958 divide the metamorphic phases into two types on the basis of the pressure, that is contact metamorphism, where pressure is less than 4 kilobar, and regional metamorphism, where pressure is more than 4 kilobar. Turner in 1968, 1990, 81 has described the classic account of contact metamorphism, where temperature induced recrystallization is important. The contact metamorphism is observed in basic or mafic rocks which have been intruded by magmatic bodies like felsic or basic magma in order of increasing temperature. The low temperature or contact metamorphism or Abukama type of metamorphism are as follows: albite epidote hornfels phases, second hornblende hornfels phases, third pyroxene hornfels phases, and fourth sanidinite phases. Are basalt and andesite. These rocks constitute a major portion of oceanic crust and also widespread in geosynclines in the form of basaltic flow, pillow lavas, sill, and dikes. The main constituents of basalt are calcic plagioclase, anorthite 40 to anorthite 70, and clinopyroxene, along with olivine and orthopyroxene. Accessory minerals are often sphene, ilmenite, rutile. The anorthite content varies from albite epidote hornfels phases to sanidinite phases. The temperature of metamorphism increase from albite epidote hornfels phases to sanidinite phases. They may pass outward with decreasing metamorphic grade into albite epidote hornfels phases. In some areas, they are seen to pass inward with increasing grade of rock of pyroxene hornfels phases to sanidinite phases. There will be temperature increase from outer fringe zone to inner areoles or zone, and mineral reaction take place in the progressive way. With increasing temperature, more high temperature minerals are formed. Several areoles or zones of increasing temperature of magma are recognized, which also depend on the depth of the intrusive, thickness of the intrusive, and diameter of the intrusive magma, etc. The bulk composition can be defined in terms of the component CO, Na2O, Al2O3, MgO, FeO, and SiO2. Normally, ACF diagrams are used to observe the minerals assemblages. In low pressure metamorphism of basic rocks due to the thermal effect of an intrusive rocks, different zone or contact areoles are developed, which are as follows: albite epidote hornfels facies, actinolite epidote chlorite zone, hornblende hornfels facies, hornblende plagioclase diapside zone, pyroxene hornfels facies, orthopyroxene plagioclase zone. Reaction in these progressive contact metamorphism that have been documented by petrographic evidence and investigated by laboratory works: albite epidote hornfels facies, actinolite epidote chlorite zone. This facies was introduced by Phi, Turner and Varugan 1958 to cover the mineral assemblages that sometimes appear in outer fringe of the contact areoles, and hence the mineral assemblages form at low temperature of about 300 to 400 degrees centigrade. Pressure also low in range of 100 to 3700 bars, that is less than 4 kilobar. Most of the understanding of the phases of low pressure is drawn from contact areoles developed by plutons at relatively high crustal level, post-tectonic granitic plutons cutting deformed geosynclines, filling and Archean's greenstone belts, floor underlying massive Precambrian stratified mafic, ultramafic seeds injected into virtually undeformed basins, sediments and volcanics. Chemographic phase relations. The albite epidote hornfels facies was proposed to cover mineral assemblages as they begin to form in the outermost fringe of contact areoles. Talc Mg6, Si8O20 OH4 appear as the first silicate phase in metadolomites of some areoles, and antigorite Mg3 Si2O5 OH4 serpentine has been similarly recorded in areoles in some serpentinized, for example, Telly in 1951. With such qualifications in mind, chemographic phase relation in the albite epidote hornfels facies can be tentatively depicted in the figure ACF diagrams. In the lowest temperature of this facies, recrystallization produces quartz, chlorite, albite, epidote, and with increase in temperature, actinolite appears. The important reaction Mg3 Si2O5 OH4 plus 6 CaCO3 plus 14 SiO2 give rise to 3 Ca2 MgFe5 Si8 O22 OS twice plus 7 H2O plus 6 CO2. Antigorite plus calcite plus quartz give rise to actinolite plus water plus CO2. With a slight increase of temperature, plagioclase become more calcic, anorthite 10%. The typical basic assemblage is epidote, tremolite, chlorite, albite plus minus quartz. These assemblages correspond to albite epidote hornfels facies of low pressure or greenschist facies of regional metamorphism. If further rise in temperature, talc breakdown and form anthophyllite develop to give rise to hornblende hornfels facies. Hornblende hornfels facies, hornblende plagioclase diapside zone. When the basic rocks are in immediate contact with magma or are intruded as pendant in it, the mineralogical assemblages of the hornblende hornfels facies differ from the albite epidote hornfels facies in the development of hornblende plagioclase anorthite 25 to 40% rather than albite epidote actinolite, and in the presence of diapsite in these basic rocks, the plagioclase is anorthite 25 to 40 in composition, actinolite disappear, and the sometime diapsite appears. See figure. The Cummingtonite, anthophyllite, hornblende and plagioclase form by the reaction 7Ca2 MgFe5 Al2 Si6O22 OS twice plus 10 SiO2 give rise to 5 MgFe7 Al Si7 O22 OH twice plus 4 Ca Al2 Si2 O8 trismechite plus quartz give rise to Cummingtonite plus anorthite. 7 tal give rise to 3 anthophyllite plus 4 quartz plus 4 S2O at 705 degrees centigrade 2 kilobar. Chlorite plus tremolite plus epidote plus quartz give rise to hornblende plus water. Epidote plus albite give rise to plagioclase plus water. The important basic assemblages hornblende, plagioclase, biotite, quartz, hornblende, plagioclase, diapsite plus minus quartz. The upper temperature limit marked by the formation of hypersthene by the following reaction: gaderite plus quartz give rise to hypersthene plus corderite plus water 705 degrees centigrade 1 kilobar, 755 degrees centigrade 2 kilobar, carried out by Akela and Winkler 1966. Gaderite plus quartz give rise to hypersthene plus anorthite plus hornblende plus water 750 degrees centigrade 1 kilobar, 770 degrees centigrade 2 kilobar, carried out by Chaudhary and Winkler 1967. Mg anthophyllite plus quartz give rise to anorthite plus quartz plus water 745 degrees centigrade 1 kilobar, carried out by Greenwood 1963. These reactions therefore suggest temperature range between 500 to 550 degrees centigrade to 750 degrees centigrade for this phases. This zone corresponds to the hornblende hornfels phases of low pressure and amphibolite phases of medium pressure regional metamorphism. Pyroxene hornfels phases, orthopyroxene plagioclase zone. This zone is marked by the breakdown of anthophyllite, Cummingtonite and appearance of orthopyroxene by the following reaction: Mg anthophyllite give rise to anorthite plus quartz plus water. This reaction was carried out by Evans at 760 degrees centigrade 2 kilobar. Mg anthophyllite plus phosphorite give rise to anorthite plus water. This reaction carried out by Evans at 700 degrees centigrade 2 kilobar. Other reactions are hornblende plus quartz give rise to hypersthene plus plagioclase plus minus diapsite plus water. The following important basic assemblages observed in this zone: plagioclase, hypersthene plus minus biotite, plagioclase, diapsite, hypersthene plus minus quartz, plagioclase, diapsite plus minus quartz. These assemblages are observed in Oslo Goldsmith in 1911. This zone is equivalent to pyroxene hornfels phases. Sanidinite phases. The sanidinite phases was erected by Ascola to uncover mineral assemblages whose mineralogical composition and geological occurrences so that they have formed at maximum temperature and minimum pressure of metamorphism. Ascola in 1939. Rocks of this phases are restricted to xenolith in lavas and dikes rocks and locally in contact rocks in the immediate vicinity of near surface intrusion. In this later situation, unusually high temperature have been maintained by the continuous flow of magma along the contact. Characteristic minerals in silica rich pylites, high temperature minerals like tridymite, sanidinite, Na-rich anorthite and mullite are common together with cordierite. As a result of partial or complete fusion of the pylite, a glass is sometimes present in rock of this species. These are called puchites, in which cordierite, corundum, mullite or tridymite are enclosed in glassy groundmass. Micas, amphiboles and garnet are absent. Important reaction. The important reactions occur during sanidinite phases are given below. Quartz give rise to tridymite 870 degrees centigrade at atmospheric pressure. Orthoclase give rise to sanidinite. Quartz give rise to tridymite, give rise to cristobalite. Basic assemblages. Plagioclase, diapsite, hyperthin, pressure temperature condition during thermal metamorphism of basic or mafic rocks. Lower temperature limit. The antigorite, calcite and quartz react and form actinolite plus water plus CO2. Characterize the beginning of albite epidote hornfeld phases. Mg3 Si2O5OH4 plus 6 CaCO3 plus 14 SiO2 give rise to 3 Ca2 MgFe5 Si8O22OH twice plus 7 H2O plus 6 CO2. Antigorite plus calcite plus quartz give rise to actinolite plus water plus CO2. Chlorite plus tremolite plus quartz give rise to hornblende plus anthophyllite plus water. Reaction number 6. Same pressure and temperature condition as reaction 5, 550 degrees centigrade 1 kilobar and 560 degrees centigrade 2 kilobar by Chaudhary and Winkler 1967. Upper temperature limit. The upper temperature limit is marked by the breakdown of anthophyllite, cummingtonite and appearance of orthopyroxene by the following reaction. Mg anthophyllite gave rise to anorthite plus quartz plus water. This reaction carried out by Evans at 760 degrees centigrade 2 kilobar. Quartz give rise to tridymite 870 degrees centigrade at atmospheric pressure. Pressure condition. Pressure condition ranges between few hundred bars to about 4 kilobar. The upper pressure limit is indicated by the absence of kyanite and the common presence of andalusite suggest pressure of less than 4 kilobar. Therefore, below the pressure limit of triple point of Al2SiO5 by Holdway 1971 at 501 degrees centigrade 3.76 kilobar. And second, the absence of almandine garnet and kyanite in low pressure environment of metamorphism suggest of less than 4 kilobar pressure or so during metamorphism of albite epidote hornfeld phases, because almandine garnet formed by the reaction chlorite plus muscovite plus quartz give rise to almandine plus biotite plus aluminosilicate plus water at 500 degrees centigrade 4 kilobar and 600 degrees centigrade 5 kilobar by Horsberg and Winkler 1968. However, almandine garnet is also reported from some thermal areoles by Sinner in 1962. The absence of almandine in low pressure condition also suggests pressure less than 4 kilobar. Shu 1968. Thus, absence of almandine and kyanite in low pressure environment of metamorphism suggests of less than 4 kilobar pressure or so during metamorphism of basic or mafic rocks. Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on thermal metamorphism of ultramafic, ultrabasic rocks. The following heads: Introduction, Thermal Metamorphism, Characteristic Minerals, Type of protolith, metamorphism of ultramafic, ultrabasic rocks with the help of ACF diagrams for individual phases during ultramafic metamorphism and summary. Hope it will be useful for you. Try to be regular in course. Pressure and temperature, we can divide the metamorphic phases into three types, mainly phases of low pressure, phases of intermediate pressure, and phases of high pressure. Mayasiro originally recognized three different types of phase series. First, a geolite, prehenite, pumpelite, blue schist eclogite type. Second, a typical Barrovian type characterized by green schist, epidote amphibolite, amphibolite, gaolite, characterized by paragenesis of kyanite sillimanite type. And third, an Abukama type of green schist, amphibolite, gaolite, paragenesis of Andalusite sillimanite type. Fay et al. In 1958 divide the metamorphic phases into two types on the basis of pressure, that is contact metamorphism, where pressure is less than 4 kilobar, and regional metamorphism, where pressure is more than 4 kilobar. Turner in 1968 and 1981 have described the classic accounts of contact metamorphism, where temperature-induced recrystallization is important. The contact metamorphism is observed in ultra-basic or ultramafic rocks which have been intruded by magmatic bodies like felsic or basic magma. Several areoles or zones of increasing temperature of metamorphism are recognized, which also depend on the depth of the intrusive, thickness of the intrusive, and diameter of the intrusive magma, etc. The bulk composition can be defined in terms of the composition Mg, Fe, MgO, FeO, CO, SiO2. Normally, ACF diagrams are used to observe in mineral assemblages in order of increasing temperature. The low pressure of contact metamorphism or Abukama type of metamorphism are as follows: albite epidote hornfeld phases, hornblende hornfeld phases, pyroxene hornfeld phases, and sanidinite phases. Characteristic minerals: the ultramafic, ultrabasic rocks are pedotites. The main constituents these rocks are olivine, pyroxene, orthopyroxene, and clinopyroxene, plus minus calcic plagioclase. Accessory minerals are often ilmenite or rutile. The best example of contact metamorphism of ultramafic rocks is represented by serpentinite's body. The temperature of metamorphism increased from albite epidote hornfeld phases to sanidinite phases. They may pass outward with decreasing metamorphic grade into albite epidote hornfeld phases. In some areoles, they are seen to pass inward with increasing grade into rock of pyroxene hornfeld phases to sanidinite phases. There will be temperature increase from outer fringe or zones to inner areoles or zones, and mineral reaction take place in a progressive way with increasing temperature. More high temperature minerals are formed. The serpentinite constituted of antigorite plus olivine plus diopside plus chlorite plus magnesite. This assemblages was subjected to contact metamorphism and developed the following zones of metamorphism. First, antigorite olivine diopside zone. Second, antigorite olivine tremolite zone. Third, talc olivine tremolite zone. Fourth, anthophyllite olivine tremolite zone. And fifth, inertite olivine diopside zone. Let us take first antigorite olivine diopside zone. This zone represents the assemblage of ultramafic, ultrabasic serpentinite body formed due to the hydration or activity of water, low temperature metamorphism of ultramafic pedotites, dunite, pyroxenite, etc. rocks. The important reactions are anorthosite plus water give rise to serpentinite plus quartz. Phosphorite plus water plus CO2 give rise to serpentine plus magnesite. Another reaction is phosphorite plus water give rise to serpentine plus brucite at 380 degrees centigrade 2 kilobar. The possible assemblages of the serpentinite protolith are antigorite, brucite, dapsite, phosphorite, antigorite, brucite, olivine, magnesite. Second, antigorite, olivine, tremolite zone. The univariant equilibrium connecting these assemblages is antigorite plus dapsite give rise to tremolite plus phosphorite plus H2O. This reaction was carried out by us Evans in 1970. Third, talc olivine tremolite zone. With increasing thermal effect, antigorite becomes unstable and the talc appears by the reaction serpentine give rise to olivine plus talc plus water 460 degrees centigrade 2 kilobar. According to Wiley 1967, the equilibrium data for serpentine reaction are 500 degrees centigrade 3 kilobar, while serpentine reaction 540 degrees centigrade 2 kilobar. These assemblages correspond to albite epidote Hornfeld phases of low pressure or Green's phases of intermediate pressure, regional metamorphism. Fourth, anthophyllite olivine tremolite zone. The formation of anthophyllite is talc plus olivine give rise to anthophyllite plus water. Greenwood 1963 gave 675 degrees centigrade 2 kilobar. Another reaction is talc give rise to anthophyllite plus quartz plus water 705 degrees centigrade 2 kilobar. Fifth, anorthosite olivine dapsite zone. This zone is marked by the breakdown of anthophyllite. Anthophyllite plus phosphorite gave rise to anorthosite plus water. Other reaction, tremolite plus phosphorite give rise to anorthosite plus dapsite plus water. This zone is equivalent to pyroxene Hornfeld phases of contact metamorphism or gammalite phases of regional metamorphism. One can see the pressure temperature diagram for sequence of mineral reactions if ultramafic bodies are spinel, bearing and hence contain large amounts Al2O3 and MgO, and sapphire Mg2 Al4 SiO10 is formed within this zone. The sapphire is formed by the reaction anthophyllite plus spinel plus quartz give rise to sapphire. Anorthosite plus spinel plus quartz give rise to sapphire. This assemblage is stable at 700 to 750 degrees centigrade at low pressure. Today, in this lecture, we have discussed about the thermal metamorphism of ultramafic rocks. I have covered this topic under the following heads: introduction, important reaction, ultramafic assemblages. I believe this lecture was useful for you. Try to be regular in course. For further studies, please read the textbooks, references and link given in the text. Thank you very much.